We welcome the first speaker of our session, Carsten. Okay, please.
Yeah, good morning, or well, for you guys, probably more good afternoon or good evening, depending on from where you tune in. And thank you, Mika, for giving me this opportunity to present to you our most recent results on our strongly interacting Bose-Fermi mixture. My name is Carsten. I'm a postdoc here in the Spectroscopy group at MIT. And before we jump into the topic, please really feel free to interrupt me right away and frequently so that we can have an ongoing discussion throughout the talk if there's anything that you would like to discuss in further detail or that I should clarify and so on. And yeah, so before we jump right into Bose-Polaron quasiparticles, let's start with something else that we're all very, very familiar with, namely the success of quasiparticles. And well, let's start with something that's even simpler, namely, as you can see here, the Schrödinger equation, which all of you know has been an incredibly successful tool at describing the quantum properties of single quantum mechanical particles. We can calculate energies and time evolutions to infinite precision, basically, as long as we restrict ourselves to a system with very few particles. However, as you also know, as we keep adding more and more particles, and in particular, as these particles become stronger interacting, this approach pretty much completely breaks down to a point where at sufficiently many particles, it's absolutely intractable to even numerically calculate the dynamics or the static properties even of these systems from an ab initio calculation of each individual particle. And this is, of course, exactly where the success of quasiparticles has been, or where quasiparticles as a concept has been incredibly successful over the past decade, namely that in such cases, we can typically describe the system very well, but first getting the energetic ground state and then describing the low-lying excitations on top of such a strongly interacting ground state in terms of weakly interacting quasiparticles. Now, just to give you two examples that I'm sure you have all seen before of quasiparticles, we of course have phonons, which is just when we have a distortion in an ionic lattice, we can describe these distortions using phonon quasiparticles. And on the other hand, Fermi liquid theory, where if we have a degenerate Fermi gas, the excitations on top of such a degenerate Fermi gas, we can then again describe as in terms of weakly interacting quasiparticles. Now, while describing strongly correlated systems in terms of quasiparticles at sufficiently low temperatures is something that indeed has been very useful and successful over the past years. So what over the past decades, more to say, what I've drawn here is an example of a generic quantum phase diagram. So on the y-axis, we have temperature, and on the x-axis, we have some generic order parameter. So we could have a quantum phase A, which may be a quasiparticle that has more of a wave-like character in one corner of this phase diagram, and whereas we could have a different phase with a completely different quasiparticle in different the corner of right. So now, more recently, attention has been drawn in the region between two of these quantum phases, where the phases can coexist and compete with each other, and in particular, when we have an underlying second order quantum phase transition, which we also refer to as a quantum critical point. Now, Sashdev, for example, beautifully explains in this textbook that such an underlying quantum critical point can indeed give rise to a whole quantum critical regime at finite temperature, where the system obtains non-trivial universal character. And so, besides other things, one of the main characteristics of these quantum critical regimes is indeed that the thermal equilibration time of the system it will be inversely proportional to the temperature and independent of any microscopic detail. And so if the thermal equilibration time of the is inversely proportional to temperature, that also means that your lifetime of whatever excitations you might have or try to have in the system will be set by the temperature, which I guess kind of makes intuitive sense that because in this regime, you don't really have any other energy scale left than the temperature to scale with. Now, this is not just an abstract concept, but rather it finds direct application to explain the so-called strange metal phase that we see in cube-rate superconductors. And so I'm sure many of you have seen this phase diagram plenty of times before, but let's still again walk through it. So we have again temperature on the y-axis, and now we have the doping of the system on the x-axis. And of course, if I have a fully doped, if I have a fully filled lattice at sufficiently low temperature, I would end up in an antiferromagnetically ordered phase. However, and then if I dope the system enough, so if I have few enough electrons left, I would get something that is very well described by a Fermi liquid theory. Now, in between, however, if we go to the lab, or not we, but solid state physicists go to the lab and measure the resistivity, they actually see something that is a little bit peculiar, namely that the resistivity grows linearly with temperature and directly given by a very fundamental quantum mechanical scale. So it's just kBt over h bar. And indeed, the resistivity grows to values that are so high that indicate that the mean free pars of whatever is the charge carrier here is shorter than the lattice spacing itself. And so at this point, we really should talk about a breakdown of the quasi-particle, because if you can't even propagate for a single lattice spacing, it's not a very useful concept to begin with. Now, I'm pretty sure that you're also familiar with the fact that it's very hard to now take one of these cube-rate superconductors, slice it open, put it under a microscope, and really study what exactly is going on in detail. And this is exactly where with ultracold atoms we come into play, because we have this pristine platform where we can really precisely control the density, the temperature, the interactions, in principle also the quantum statistics of these systems, and then study in a very clean and reproducible way whatever Hamiltonian we are currently looking at. Now, furthermore, since this quantum critical regime is predicted to have universal character, you don't really have to mimic the Hamiltonian of cube-rate superconductors. We instead can probe any system that has an underlying second-order quantum phase condition, as this is predicted to always give rise to these quantum critical regimes. Now, so this brings us then to the quasi-particle of our choice, which is the Bose-Boron quasi-particle. And so I'm sure most of you are already experts on the Bose-Boron quasi-particle, but let me still give you a very short introduction and historic introduction to the problem, which was, is there? I see things flying through the room, but it doesn't seem to be a question.
Yeah. Well, I mean, this is not a physics question, or maybe it is. But I mean, why do you have Landau in prison? Because
oh yes,
I mean,
no,
is it for a purpose? I mean, does it mean something that quasi-particles are not good?
No, I really apologize for this. I didn't realize, and I didn't swap out the picture in time. I didn't realize when I first found this picture that this is actually him in prison. This should have been replaced by now. There's no relation to this. Yes. Because as far as I understand the story,
I don't need to apologize. Most of physicists were in prison, so I mean it's okay. It's even nice to see an unconventional picture, but not the textbook.
Okay. I'm glad if nobody is offended, but it definitely
looks young and nice, and you see even hair is still much nice.
All right. Good. So yes, so it all started with Landau asking a simple question: what happens if I have a positively charged ionic lattice and I place a single electron in this lattice? Well, and as obviously the interaction between the electron and these ions will certainly deform this lattice crystal to a point where the electron at strong enough interaction can actually create its own bound state. Now, it was then Picard who pointed out that indeed we don't really have to worry about the microscopic details of the lattice, but instead we should replace the lattice simply with a phonon bath, and then the coherent interaction between electrons and phonons will then lead to a dressing of the electron into these quasi-particles, which then Picard coined the Bose-Boron quasi-particle. Now it's also, since a phonon-electron interaction is something that's very generic in solids, it's not very surprising that the Bose-Boron quasi-particle finds a wide application, as for example in the colossal magnetoresistance or helium impurities, helium-3 impurities in liquid helium-4, or more exotic materials such as organic field effect transistors. Now, it was also very early pointed out that indeed ultracold atoms are an ideal platform to study such Bose-Boron quasiparticles, because we can replace the electron impurities with simply atomic impurities and replace the phonon mass by a Bose Einstein condensate, which at least at low momentum actually has a phonon-like excitations. And so this system would then allow us to study what happens in particular as we approach unitarity, as we can control the interactions very well. Right. So at the start of our study, actually, it was a very open question: what really happens once you tune in, once you go to unitary interaction strength? Because in contrast to the Fermi Polaron, which has been very well studied and is very well explained by the Chevy ansatz, in the bosonic case, we can, in principle, at unitary have infinitely many bosonic excitation coupling to these atomic impurities. And so this was one of the things that got us excited about the problem in the first place. Now, I've introduced the Bose-Boron as a quasi-particle. What I've not really told you about is how we can link now this Bose-Boron quasi-particle to quantum criticality. And so let's think about it a little bit more general in terms of the Bose-Fermi mixture, which is in general described by 5 parameters, namely the chemical potential of the bosons, the chemical potentials of the fermions, the interaction between the bosonic particles, the interactions between the bosons and fermions, and the mass ratio between the bosons and the fermions. Now, technically, if we wouldn't be working with just spin polarized fermions, we could also have some Fermi-Fermi interactions, but since we are only working with spin polarized fermions, I'm neglecting that right away. Furthermore, we can also drop actually 3 more of these coefficients as we are working with the BC, where the chemical potential is very close to where the chemical potential is very small. And indeed, the boson-boson interaction is also very small, so we can neglect both of these coefficients. And of course, experimentally for us, it's very hard to tune the mass ratio of a given experiment. So I'm also not going to further talk about the mass ratio in itself. Now, this allows me then to directly draw to you our 2-dimensional phase diagram, where what I've drawn here on the z-axis is the number of fermions in the system, and this is exactly our order parameter of the system. So before you read too much into this 2-dimensional phase diagram, let's for a second consider a case where I just have fermions alone, and I would tune the chemical potential of these fermions. Now, at negative chemical potential, there are of course no fermions around, and so the state that I have is just a pure vacuum state, right? And as I cross now the chemical potential from negative to positive values, I will start having more and more fermions in my system, which therefore qualifies as the 2nd order quantum phase transition, going from a vacuum state to a Fermi gas with finite density, with the fermion number being the order parameter directly. Now, in our case, again, we have here the chemical potential of the fermions, and on the other axis, given an inverse K and A, the interaction strengths between the bosons and the fermions. And as you can see, we have, again, 2 phases. In this case, it's the BEC plus a Fermi vacuum and the BEC plus a Fermi gas. Now, the transition of the 2 systems is not just at 0, but instead it is exactly shifted by the Bose-Boron quasi-particle binding energy. Right. And so since this is a 2-dimensional phase diagram, now instead of having a single quantum critical point, we obtain a quantum critical line. All right, so with that out of the way, I hopefully have introduced the Bose-Boron quasi-particle, quantum criticality in general, and how the Bose-Fermi mixture indeed qualifies as a system with an underlying quantum critical point, or specifically quantum critical line. Let's go to the lab and have a look at what we can probe as we approach this quantum critical line. So in the lab, we work with sodium and potassium. Sodium is our boson, and potassium-40 is our fermionic impurity. Both species are simultaneously trapped in a crossed optical dipole trap. We then simultaneously evaporate both species to temperatures of about 100 nanokelvin, at which point the boson condensed in a BEC. And then in the final step in this set of experiments, we ramp on a species selective dipole trap, which tightly confines the fermionic impurities within the BEC. Now, at this point, we can take absorption images of the system and obtain images such as the following that you can see here. So this is the BEC, and here we have our impurities. And at the densities where we are typically working at, the impurity concentration reaches about not even 1%. So we are really talking about a very deep single impurity limit. Now, furthermore, if you were to ask me to give you one slide to show you why it's an absolute pleasure to work with sodium and potassium, that would be a slide similar to this. Because what you see here, this is the Feshbach resonance landscape of sodium and potassium, where the difference between the blue and the red trace are two different spin states of the potassium interacting with the sodium. And what you can see is that we have a couple of very broad or fairly broad Feshbach resonances overlapping. And this typically provides us with any kind of interaction strength scenario that you would like to have for your study. In particular, in this case, what we are using is the situation where in the initial state, our fermionic impurities are strongly attractively interacting with the BEC. So they will happily form Bose-Boron quasiparticles. And then we eject them into a final state that goes through a zero crossing. So it's a truly non-interacting final state, allowing us to very carefully measure the properties of the initial state. Yes, so yeah.
This sodium state like
58 Bohr, so it's very weakly positive.
flat. Flat. That won't depend on the
I'm not fully understanding the question. Sorry.
magnetic field independent.
It's pretty independent. Sodium doesn't have a Feshbach, like in that region. The sodium has no Feshbach resonance, so it's completely flat.
Thank you.
But it's a great question because and that I mean that goes completely in a different direction. But since you already bring it up, and we originally got interested in the question, like, can you have infinitely many excitations on top of the fermions? Richard Schmidt recently published a paper where he exactly shows that no, this is not possible because of this weak repulsive interaction. Bosons actually don't really like to be on top of each other. And yeah, so even though it's weak and repulsive, it's still very relevant for the problem. All right, right. So let's go to the lab, do the experiment. And so to do the experiment, we simply apply an RF pulse that is resonant with the potassium atomic transition. And if we apply this RF pulse and look at what kind of fraction of atoms we transfer, well, you immediately see a striking feature, namely that if the RF drive is resonant with the pure atomic transition, then we don't really transfer any of the impurities that are located within the BEC, but rather we only transfer impurities that are out of the BEC. And so you actually have to increase the RF frequency by quite a bit before you start transferring the impurities that are deeply located within the BEC. And the reason, of course, is that these impurities form Bose-Boron quasiparticles, and your RF drive has to provide that additional binding energy before you can transfer them into the non-interacting final state. Now, I also should point out that indeed the transfer in the center actually lasts for quite a while. And so we have not just obviously probed this at 5 different frequencies, but rather we have probed this across the whole frequency range. And what I'm plotting here is just the central transfer of these RF spectra as a function of the axial position. So exactly this position here that you see on the left side. So now, again, to reiterate, impurities that are not located within the BEC transfer exactly at the atomic transition, but then as the impurities enter the Bose Einstein condensate, the system can substantially lower its energy, and we see this as an increased RF frequency. So we have to provide this binding energy to transfer the impurities to the final state. Now, if we interpret our data under the local density approximation, this gives us then access to the properties of the Bose boson as a function of the local chemical potential of the boson, or also or equivalently as a function of the local T over Tc, so as a function of the local temperature of the Bose gas. Now, if you just look at this in laboratory kilohertz units, we indeed observe that we go from a strong shift back to no shift as we go above Tc. But this is a little bit of an unfair comparison, because as T over Tc changes here, so does the local density. And so really to get a more meaningful comparison between these data sets, we have to divide, divide by the degeneracy energy scale En, here given by Kn square. So for those of you that are not super familiar with this, this is basically like the Fermi energy and Fermi gases. And now, as we do this, you see a very striking, well, one very striking feature and perhaps a second feature already popping up. Namely, first of all, as we approach Tc, our spectra tremendously broadens, whereas then above Tc, they just shrink basically directly down back to our Fourier limited width. It just comes from the RF pulse. And then second, you also observe that maybe there's a little bit of a shift in the central transfer of our spectra. So if we summarize these findings and interpret indeed the peak of our spectra as the binding energy of the polaron, and the width of these spectra as the inverse lifetime of our polarons, we can observe the following. And I should point out that at this point that we have not only probed the system here at near unitary interaction strength, but also starting at weaker interaction strength. So at weaker, going from weak to strong interaction strength, as you would naively expect, the binding energy of the polaron increases, where then at our strongest interaction strengths, we actually see what I indicated before. We see at first an increase, kind of a saturation plateau, and then a very sudden jump back down to zero binding energy as we cross exactly T over Tc equal 1. And now let me give you a little bit of intuition why at least some features of this is what we expect. So at zero temperature, we would expect that something like a Chevy ansatz calculation should do a fairly decent job. So we're happy that at least we can somewhat kind of connect to this Chevy ansatz calculation. And then at at high temperatures, where the temperature is actually larger than the energy spacing between the attractive and repulsive branch, then of course we should not see any more shift at all. So indeed the shift should go down back to zero. Now at this point, I would like to draw your attention more to the lower plot, which is the inverse lifetime. And I should point out that actually Jesper Levinson and Mira Parrish, as well as Georg Grun, have indeed predicted a temperature dependency on the Bose-Boron binding energy. Our experiments are not a perfect quantitative agreement, but qualitatively there definitely is a temperature dependency. Now, at this point, I want to draw your attention more to the lower plot, where I plot the inverse lifetime of these Bose-Boron quasiparticles as a function of T over Tc. And indeed, we do see a linear behavior, and not just any linear behavior. We are seeing a linear behavior exactly on the order of kVt over h bar. So indeed, this is one of the hallmarks of quantum criticality that I've outlined before, that the inverse lifetime should be directly proportional to temperature. That the lifetime should be, the inverse lifetime should be proportional to temperature. Furthermore, our lifetime actually, this inverse lifetime very quickly grows to values which exceed the binding energy of the Bose of our measured binding energy. And now at this point, again, it becomes kind of a meaningful picture to talk about the quasi-particle to begin with, because if the lifetime is less than the energy, we're again left with something that does not really resemble a well-defined quasi-particle to begin with. And so we are indeed seeing the breakdown of the quasi-particle as we increase the temperature. I'm
sorry.
Yes.
I'm sorry. Question here.
Yes.
I'm sorry. I'm a bit lost. So Tc is what?
Sorry.
Critical temperature of what?
Of the Bose gas.
But on the kind of second slide, the third, you showed the picture that your second order transition happens between vacuum and and
Precisely.
and finite Fermi density kind of.
Yes.
So okay.
Yes. So we are not scanning that. We're not scanning here the
chemical potential. So it's not a
exactly.
chemical potential. Okay.
So let me just go back to this generic phase diagram. So what in some sense we are not scanning across here. We're starting somewhere here and we're going that axis.
I see. Okay.
So we're not directly at unitarity. We're very close, and then we're scanning upwards, and we are entering this pretty much right away. We're entering this quantum critical regime, and then we see this linear dependency in temperature.
So sorry again. So you said unitarity. So what your system at this quantum critical point? What would that be? Can you explain?
Yes. So you mean this, right? So yeah. we're close to that point at a fixed chemical potential of the fermions, and now we're scanning, which I haven't drawn here, the temperature as you kind of saw it in the other diagram.
I see.
So it is a system where you have a Bose gas.
So ideally, you would like to be at the critical point and then increase temperature from there.
Mm-hmm.
But you are a little bit shifted.
Exactly. If you were, then right from the start, it would never be a form any quasi-particle, right? And then it would just always be in this quantum critical regime. And so what we are doing, we are very close to unitarity, and indeed, kind of like it's hard to say whether we are always linear. I mean, it looks like we are always linear. So I could argue we are from wherever we can probe, we are within the quantum critical regime, and now we are just increasing the temperature, and we are observing the inverse lifetime. So it's a very analogous measurement to what you do in when you measure resistivity in cube-rate superconductors.
Okay, but what about, so for the Fermi Polaron at unitarity, you always have a good quasi-particle, even, I mean, and at what you call the quantum critical point, which is the single impurity, right?
So I would argue at zero temperature, I should be anyway fine. I would argue that like once the inverse lifetime exceeds the binding energy, that's the point where I cannot talk about a well-defined quasi-particle anymore.
Okay, so you are just saying that if you increase the temperature enough, then you destroy the quasi-particle.
So what I'm saying is I see a linear scaling of the inverse lifetime with the temperature, indeed, and I'm saying that once this inverse lifetime exceeds the quasi-particle binding energy, then I observe a breakdown of the quasi-particle. Yes.
Okay, but still, I mean, isn't the situation quite different from the one of a quantum phase transition? Because here, here, when you go to zero temperature, you get well-defined quasi-particle, even if you are at the what you call a quantum critical point. Well, if it's a quantum phase transition, that's not the case.
So you're saying that this is true for the Fermi Polaron,
but probably for the Bose Polaron as well.
But I mean, there is an underlying second order quantum phase transition, right? Which is exactly happens at the binding energy of the Bose Polaron quasi-particles. So
yes, but it's I'm wondering whether it's in a way trivial quantum phase transition, if you want, or different from the generic one.
I would argue, like as far as I know, any second order quantum phase transition will give rise to this. I think like I earlier mentioned, Sashev also goes through like these examples exactly of a Fermi gas and a Bose gas in his textbook, where you have a transition between a vacuum state and a state of finite density.
Okay.
So,
okay, thanks. Yeah. Anyway, go ahead.
No,
yeah, thank you.
But I'm glad for the question. So yeah, maybe afterwards we can keep discussing on that.
Sure.
Right.
So maybe can I ask a quick question? So you are you
Yes.
saying you'd see the same behavior for the Fermi Polaron as well?
So I shouldn't answer this probably because I'm not an expert on the Fermi Polaron. But I know that the Fermi gas itself also has a second order quantum phase transition. Yes.
Yeah, I guess it's just that you were talking about this vacuum transition, and
Right.
there doesn't seem to be from the way you described it, there doesn't seem to be a real difference between a fermionic medium and a bosonic medium, or
Yeah. Yes. So like I said, so in such a textbook, he goes through both examples of the Bose and Fermi gas. I think he starts even with the Fermi gas as it's a little bit simpler. Yeah, because you don't even have on top the phase transition of the BEC.
Okay, so it's just that in the fermionic case, it goes like T squared. So the lifetime.
Oh yes, you're right. Yes, that is. So this. Yes, where this is just Fermi liquid theory, right?
Mm-hmm. Yeah, that's right.
Yes. Yeah. So yeah, I cannot draw directly the connection to the Fermi Polaron, I must say.
It's okay. I'll let you continue. Yeah.
No, it's a great question. Thanks. Yeah.
All right.
All right. Great. Yes. So yeah. So coming back to the Bose-Polaron. So since in our case we don't have a complicated high-C cuprate superconductor, but we rather have a Bose gas with fermionic impurities in there. We asked ourselves the question: well, can we actually get a simple estimate why this should indeed be scaling linearly with temperature, just from first principles, kind of. And so if we go in with the assumption that the BEC addresses the impurity but doesn't further provide any scattering, so then the only thing that is left that these Polaron quasiparticles can scatter with are indeed the thermal excitations of the bosons. And so if we write them down as just the scattering rate as n sigma v, and use a Bose gas at unitarity and keep track of all the temperature dependencies, we indeed observe something, or we indeed get something that is directly scaling linear with the temperature from the fact that the fermionic impurities can scatter with the thermally excited bosons.
How is it important that the impurity is fermionic? If you
not at all.
So it's not at all. Okay.
Not at all. It just happens to be that for us this is more convenient. Right. So the fermions are spin polarized and so dilute that they completely ignore each other. So there's no evidence of the Fermi statistics so far.
Mm-hmm.
Okay. Yes. And so this behavior indeed was also seen recently by Richard Schmidt and Michael Fleischhauer. We did a more rigorous calculation in our back of the envelope calculation. They also observe this linear dependency on the inverse lifetime as a function of T over Tc at unitarity. So yes, so to the experts of you in the audience, you've probably already noticed that our spectra show this tail towards very long, very high frequencies, and indeed this tail tells us more about the short range correlations, which are quantified here by the contact. And now the contact is a thermodynamic property that relates how the system's energy evolves as a function of the inverse scattering length. And in this series of nice papers by Xie Tan, he has pointed out that indeed the transfer of such an RF spectrum at sufficiently large frequencies is indeed directly proportional to the contact normalized by the frequency to the 3/2. Now, if we multiply our spectra by the inverse frequency, we indeed see directly a very nice plateau from which we can directly read off the contact of our Bose-Boron quasiparticles as a function of temperature and interaction strength. And so going from weak interactions to stronger interactions, the contact increases, as you, I guess, would naturally predict. And indeed, what was a little bit surprising to us in the beginning, the contact actually agrees very, very nicely with a simple Chevy-Anders calculation that we did. Anyway, all right. So this concludes. Okay. So maybe this brings us back to the initial question where before we started this this endeavor, it wasn't really clear how many excitations you would really have on top of these fermionic impurities, and indeed we only see that that even at unitarity, the number of bosons that are really in close, the excess number of bosons that are really in close proximity to the impurity is on the order of just 1. All right, so with this, I would like to conclude the part of my talk where we so far discussed the static properties of both, such as energy and the contact of Bose-Boron quasiparticles, and move on to studying the dynamics now of this Bose-Fermi mixture. In particular,
sorry,
we are.
Yes. What did you mean with this excess? What do you mean by close proximity of the impurity?
Also, Eric Bratner has this nice analogy in this introduction where he relates the contact value as kind of like how many additional bosons you can calculate from the contact, how many additional particles you have in close proximity. And so a value of a contact of 3 means that we do have 1 excess boson within 1 interparticle distance around these fermions. That doesn't mean that it's, so I don't want to say that this means that it's a single boson making up this Bose-Boron quasiparticle, right? It can still be like many bosons that are giving rise to the Bose-Boron quasiparticle. It's just that on average, the whole density enhancement around these impurities translates into a single additional impurity boson around the impurity.
Okay, thanks.
All right, so yes, so let's have a look at dynamic properties, and in particular, what we are trying to do is we are trying to study the collective excitations of the Bose-Fermi mixture and the impurity limit. And so when we talk about studying collective modes in many-body systems, we typically try to categorize the system in 1 of 2 regimes, namely one being the collisionless regime, where indeed the mean free path of our particles is much longer than the system size. So you're in the example of these billiard boards where the table is the system size, and the mean free path, the distance a single ball can travel before it will ever scatter with the second ball is much longer than the table. Now, in this case, of course, the system is very well described by simply looking at the dynamics of a single particle. And one famous example, of course, are spin-polarized ultracold fermions, which are an ideal gas. And yes. So, however, as we increase the interactions between particles, at some point we transition into a so-called hydrodynamic regime, where indeed the system's interactions are so strong that particles can continuously maintain a local thermal equilibrium, which typically happens when the mean free path of these particles becomes much shorter than the system size. And as you all know, like a classical example of such as a hydrodynamic system would just be classical fluids such as water, but of course also Bose Einstein condensate obeys superfluid hydrodynamics. And very recently, people have become excited about 2-dimensional electron fluids, which in ultra-clean material can also become actually hydrodynamic. Now, while the 2 regimes are perhaps, well, certainly the collisionless regime is very straightforward to express, while the hydrodynamic regime can already be a little more challenging if you want to do ab initio calculation of transport coefficients. Even more challenging is typically to predict exactly the point at which a system transitions from the collisionless to the hydrodynamic regime. And so we're not obviously the first ones to study the Bose-Fermi mixture or quantum fluids in a Bose-Fermi mixture. This is there's a long history of helium-3 impurities and liquid helium-4, which, however, ultimately are limited by the inherent strong repulsive interactions which limits the amount of impurities that you can actually have before the system phase separates. And that brings us, of course, to ultracold atomic Bose-Fermi mixtures. And there, in particular, there's a very beautiful experiment from you guys in Paris, where they have observed dipole oscillations of two superfluids. So we have a bosonic superfluid and a fermionic superfluid, and we see the dipole oscillation between the two species. And that way they were able to extract the speed of sound of the superfluid directly. And also what has been studied before is the case where we have a small Bose Einstein condensate immersed in a large degenerate fermionic cloud. We can then study mean field shifts of these fermions on the bosons. Now, in our case, we are in the exact opposite regime, where we have a large Bose Einstein condensate and a few Bose-Boron quasiparticles or impurities immersed in the BEC. And this, prior to our study, has actually been largely unexplored. Now, the system is pretty much the same as you have seen before. So it's sodium and potassium. We again work in this cigar-shaped trap where our impurities are immersed in the Bose Einstein condensate. We take absorption images, in situ absorption images, which allow us to measure the distribution. And to excite now collective excitations, what we do is we simply shake the trap and see what how the system responds. Now this brings us back to the Feshbach resonance landscape. So in this study, we again make use of the fact that we pretty much have a lot of freedom. And so in this case, we work in between two Feshbach resonances so that we have a continuous way of tuning the interaction strength all the way from strong attractive to zero interaction strength to strong repulsive interaction strength. Now, if for a second we neglect the fact that indeed the BEC is a superfluid and just think of the BEC as a classical gas, then indeed, just given by our density, we would expect that in a narrow regime around zero interaction strength, we would have a collisionless regime, and then around a few hundred A Bohr, the system would enter a hydrodynamic regime. But of course, the bosons are superfluid, so let's have a look at how this changes our picture. Now, the technique we employed is a spectroscopic technique where we parametrically drive the depths of our optical dipole trap for a number of cycles, and then we observe the in situ distribution of both fermions and bosons in phase with the drive after a fixed number of cycles. So yeah, as you can see in this cartoon, so we shake the trap, and then in situ we observe whether the cloud has expanded or not, depending on whether we hit any collective or other resonance of the system. So now let's first kind of get an intuition for what we are expecting to see. So if we go to the zero crossing where we don't have any interaction strengths, and we drive the fermions off resonantly, we just see the normal distribution as we see here. But then as we increase the drive frequency, at some point we hit, in this case, one of the radial modes of our collisionless gas. And so we can directly see the fermions expand here radially in size.
Could
So
you
on the other
remind,
hand-
sorry,
Yes.
Carsten, aspect ratio of the cloud?
It's about 1 to 10. So we have a fairly good decoupling between XY. So XY are roughly the same. There's also a small asymmetry that becomes important later. And Z is fairly well decoupled. All right, so in the condensate, if we do the same experiment with our bosons, we indeed see a resonance at a slightly different frequency. And now the difference in these resonance frequencies, this is just given by the difference in AC polarizability of the system. And indeed, as we will discuss also later in a bit more detail, this mode here corresponds to the monopole mode of the BEC, whereas then if we drive it at higher frequency, we again see that the bosons do not respond to the drive at all. Right. So we've of course again not just probed this at yeah.
Is still so do you excite transverse breathing mode? Why not? It's 3D still in XY direction.
So we excite in XY direction. So we shake the trap in XY direction. Yes. We can either excite it XY in phase or out of phase, which is actually becomes interesting by which one of these two modes that I'm about to explain, which one you, if you give me 1 second, I hope I answer all your questions. Because the question is like, what modes do we really excite? So what you see here at the top, this is just if we integrate out the axial direction where there's no dynamics happening in this case, we obtain these plots. And so you see here is the y-axis, the radial axis, and this is our drive frequency. And now coming back to your questions, what are all of these modes that we excite? So for the bosonic superfluid, there are 2 modes, namely, since it is a hydrodynamic superfluid, X and Y are coupled, and so we can either get the so-called monopole or breathing mode, where the radial axis extracts and contracts in phase, or we can also excite the quadrupole mode, where the 2 radial axes extract and contract out of phase. And depending on how we drive the system, so whether we excite it with XY in phase or out of phase, we can in principle tune which of these modes is more dominantly excited. Does that fully answer your question?
Yeah, I would still don't see, maybe it's my fault, big picture. Why you want to excite transverse mode, right? In this cigar is kind of narrow. Why wouldn't you look at what's going on in longitudinal? I mean, what's
yeah. So that turns out to be more set by the finite lifetime of the impurities in the system. So ultimately, like the BC side, we understand very well. So you can just take your superfluid and take a scaling ansatz, and as you actually see in a second, so we can perfectly resolve or predict all the locations of these resonances and even all these side wiggles, which is just given by the fact that we drive the system for a finite time. So you kind of get a Fourier limited wiggles. So that's kind of, that is what the BEC does. And what we're after now is what happens if you put fermionic impurities in the system and you turn on interaction strength. And so why we are not probing the slower longitudinal axis is simply that the lifetime of the impurities is not long enough for us to probe this.
I see.
So dynamics are a factor 10 slower. And so we are already struggling at strong interaction strengths to get enough signal to noise of the fermions, as you will see in a second.
The question of lifetime at unitarity, what is it?
Lifetime at unitarity is just a few milliseconds. Even less, but yeah, so it's on the order of a few milliseconds, which is still fast enough to form Bose-Boron quasiparticles, because it takes at unitarity about a few microseconds for the system to thermalize. Right. All right. So okay. So just to kind of to conclude on this slide, in the absence of interaction strengths, we do see indeed the 2 bosonic superfluid modes that you would predict from the system at twice the radial frequency, at square root of twice the radial interrupting frequency. And for the fermions, you just see one of the 2 radial collisionless modes, as these are again spin polarized fermions. So there's no interaction between the X and Y axis indicated here. Yeah. All right. So let's go back and turn on interactions. And so maybe before we look at what happens to the fermions, let's have a look at what happens to the bosons. And perhaps not very surprisingly, there's not actually a whole lot happening because as we only have a few percent impurity concentration, the boson, there's no real back action of these impurities on the bosons. However, as we turn on the interaction strength, we see first a small change in the fermions response. Namely, we see a slight upshift in the trapping frequency as we go to attractive interactions. And of course, this can be very well understood in a mean field picture, where the fermions not only see the optical potential, but they see the joint potential from the optical and the mean field potential of the BEC. And so this gives you an upshift in their trapping frequency.
Oh, well,
No.
what is now along the axis? So what happens? You squeeze, you start to impose a oscillating field in transverse direction. So the cloud of bosons gets monopole mode or whatever, what's called it.
Yes.
Yeah, breathing. So blue is impurities. They're in the gas and they start to feel the motion of the gas, but they simultaneously feel the optical potential, right? So
exactly.
And they start to oscillate. What is along y-axis on these blue curves?
So y-axis is the relative width of the cloud. So coming back to these pictures, that's
I see. So this,
so it's the relative width as we change the drive frequency.
I see. So for some frequencies, the impurity gets broader, but this relative width is integrated over oscillation period, right? Because I don't know whether this cloud spreads and shrinks, right? So you take an integral over period.
No, not an integral. So what we do is we drive for a certain time, and then we look at the end in phase with the drive. So at this point, we take a snapshot in situ.
But in different points, the width is different.
Yes, exactly. Because I mean, that's just
relative.
If
I see. It's
exactly
the relative width of impurity to cloud to the width of bosons. So that's it.
So no, to the unperturbed width.
To the unperturbed width.
So if you drive off resonant, so far off from any resonance, right? You just like the system doesn't respond, so it just like maintains its normal width, and then as you approach whatever resonance, you will see an increase in the width after the drive.
Yeah, I see. And the time is not on this picture because of the question which you asked.
No,
right?
so we are not. So you can either study system in time, which I also have a little bit on later, or you can study them in frequency, right? So and for us, it's more interesting to study them directly spectroscopically in frequency space because we can indeed directly distinguish between all of these modes. So that's kind of like that's like why we really like this spectroscopic probing technique, because you can directly like just from the value of your frequency, you can directly say, okay, this must be the monopole mode, this must be the quadrupole mode, and this just given by the AC polarizability is it must be the fermion's own frequency. Yeah. And so as we increase the interaction strength, exactly as you say, the fermions now see not only the optical potential, but also a mean field. So this is still very weak attractive interactions, right? So now where mean field is a very good approximation. So the fermions just see the joint potential. And so of course, their trapping frequency in the center is higher. And so we see an upshift in that frequency, right? But then as we increase the frequency even further, and now probably you see more why we enjoy the spectroscopic way of probing the system, not just looking at it in time, we can directly see the fermions not only responding at their own frequency that is maybe mean field shifted, but rather we directly see a response of the fermions at the superfluid modes of the BEC. And now, in principle, there are two ways you can explain this, and this is still actually an interesting and to a certain degree open question. So in one case, you can say either, well, this is a mean field, if you want to think still in terms of mean field potential, at these frequencies, of course, that potential will also oscillate, right? Because that's what you see here on the left side. And so if the fermions can adiabatically follow this oscillation, they will also expand and contract in size, right? So a mean field picture would also predict this, right? And this
frequency 1 is the frequency of the potential oscillation, right? So like
it's twice the radial frequency
twice.
of the boson.
Yeah, twice. Yes. Okay, 2.
Yes.
So yeah, yes. So yeah, it's just normalization. I see. Yeah.
Yes. Exactly, and this is then square root of that.
Well, yeah.
Okay, so we see the fermions exactly respond to these modes of the BEC. And so like in principle you could say if I'm at zero, if you want to think about a zero temperature explanation, then mean field is the only thing that directly mean field could explain you this, because as this mean field potential shakes, the impurities which are traveling faster than that shaking, they can kind of adiabatically follow this, and so you would expect to see also the response of the impurities at this frequency. But then there's a second explanation, which is a little bit more difficult to calculate in the end. This is of course a finite temperature BEC, right? So there are thermally excited bosons, and these of course can also imprint the dynamics of the BEC onto the fermionic impurities. And I will come back to that in just a few seconds. As we increase the interactions even further, we indeed actually completely lose the response of the fermion's own frequency, and we only see the fermions respond to the BEC's modes. All right, so now we've not just probed this at a few interaction strengths, but indeed we have probed this across the whole attractive to repulsive interaction landscape. So what you see now here, each of these slices is one of these spectrograms that you have seen before. So we are seeing in color coded the width, and now in the y-axis, this is again the frequency normalized by the radial boson frequency, and then on the x-axis we have the interparticle the boson fermion interaction strength. And so close to zero interaction strengths, we indeed see kind of this linear dependency of the mean field potential of the BEC. So we either see an upshift or a downshift and the fermions response. But then very quickly we see on both sides actually only the fermion response to the BEC modes. And so something that we could actually do numerically is we could take the dissipationless Boltzmann-Wassler equation and put the BEC with its scaling ansatz and its modes in there. And indeed, we see a very good agreement between our experimental data and the simulation from based on the dissipationless Boltzmann-Wassler equation, which would indicate that indeed we see a dissipationless flow of these impurities in the Bose-Fermi mixture. However, I want to point out that of course this is a finite temperature BEC, and so it's not clear if that is really enough to describe the system, because as you keep increasing your interaction strengths, of course at some point these thermally excited bosons will become hydrodynamic with the fermionic impurities, and indeed you would see the same response. So with this we cannot really easily discriminate this. And so indeed right now together with Kushal and Pavel, two of Eugene's PhD students, we're trying to solve the finite temperature Boltzmann-Wassler equation of the full Bose-Fermi mixture with a full scattering integral. But this is a work in progress, so unfortunately I cannot show you already the results on that front. However, what I can do, of course, in the lab is I can go back and take my system and now increase the temperature and see what I see, what will happen. And now what we do indeed is we keep the absolute temperature constant, but we change the condensate fraction by just lowering the total number of bosons. So as we change the T over TC here, what we really do is we simply change the condensate fraction, right? So let's first look at the bosons themselves, because they already show something more interestingly this time. So as we increase the temperature, first things start to wash out a little bit, but then as we have sufficiently many thermal excitations, we can actually directly spectroscopically observe a new resonance. And now this is something that I've hinted at before, but I've not fully explained. Our trap is actually not perfectly round radially. So we have a difference in the X and the Y trapping frequency, which for the BEC doesn't really matter because we get a response at the geometric mean of the two radial trapping frequencies. But of course, once we have thermal excitations that are more particle-like excitations, these particle-like excitations, they're again just a thermal collisionless gas. And so they will respond just at the bare trapping frequency, which in this case, I think is omega y. And so that way you can directly observe all three modes. So the two BEC modes and the thermal excitations, which behave more like particle-like excitations spectroscopically. So as we approach TC and in particular beyond, of course, this is the only mode that survives. And so now let's have a look at what happens on the side of the impurities. Now, as we increase the temperature only a little bit, where we don't really see a response of the bosons, we already see a very strong difference in the fermionic response, where you kind of see a hint of 4 different resonances, namely again the two BEC modes. But then you already see kind of a hint of the thermally excited bosons, as well as the fermion's own frequency. And now that hint becomes more pronounced as we increase temperature even further. And now I want to pause here for just a few seconds, because at this point, because the way that we probe this, as I mentioned earlier, is that we change the condensate fraction, but the total number of thermal excitations always stays constant in our system. And what we see here is that we very clearly see a response of these fermionic impurities at the thermal excited boson frequency, which tells us that the fermionic impurities can indeed become hydrodynamic with the thermally excited bosons, which emphasizes the question that probably to fully explain the lowest temperature diagram that I've shown up here, you also need to understand the role of the thermal excitations in the system. Now, as we keep increasing temperature even further, especially above TC, density of the whole system drops. And so at this point, we simply see fermions respond at their own frequency and nothing else. All right, so I hope at this point I've convinced you that indeed we can observe we can indeed observe a dissipationless flow of the fermionic impurities in the BEC at sufficiently low temperatures and sufficiently low interaction strengths. And then I've also shown you that these fermionic impurities do indeed become hydrodynamic with the thermally excited bosonic particles. However, so far we have completely neglected the question of the BEC's critical velocity, namely the BEC's speed of sound. And so, and this is not an accident, because this set of experiments was designed so that there is no relative center of mass motion, and indeed the thermal velocity of the fermions is sufficiently below the speed of sound that the role of speed of sound never comes into play in any of these measurements. But just in the last few seconds, maybe to show you that we have devised a slightly different experiment where we have excited dipole oscillations by simply making them oscillate in a spatially displaced harmonic potential. And now in this case, we can exactly engineer situations where we have head-on collisions between the fermions and the bosons, where then the relative velocity can exceed the speed of sound. So in the absence of interaction strengths, they happily oscillate at their own trapping frequency, which is again just given by AC polarizability. You can directly see this very nicely in the spectrum on the right-hand side. And so let's go back, turn on interaction strengths, and see what happens. Well, first of all, we see dampening, but then already in the spectrogram, you kind of start seeing that something is already starting to respond at the BC frequency. And indeed, as we increase the interaction strength further, the fermions happily oscillate together with the BEC. So that's a little bit, so does it just mean that we see the exact same thing as in the collective excitations, where at strong enough interactions, the fermions inherit everything of the BEC and that's the end of the story? Well, no, obviously not, if that's the way that I asked the question, because we have to look a little bit more into detail, because what we have to look at is really the fermion velocity in the rest frame of the BEC. And so here, this is just the same data from the last plot. The color plot is the fermion oscillation, and the black line is the BEC oscillation. So if we go in the rest frame of the BEC, we at weak interaction strength see them just oscillate all over the place. And here shown with the dashed black line and the gray shaded area is indeed the critical velocity of the BEC. But as we increase interaction strength, very quickly we do see the relative velocity does not go down to 0, but instead it becomes capped exactly at the at the speed of sound of the Bose Einstein condensate, which is pretty cool to see, because that means that our fermionic impurities can kind of freely propagate in this BEC until they are accelerated to a point where the velocity exceeds the speed of sound, and then they become supersonic, can lower their momentum by emitting phonons into the BEC, slow down, and therefore then again move happily together with the BEC. And so as you also see, the red line is actually an ab initio calculation from Kushal, which agrees remarkably well with our experimental data, also across the repulsive side, which I don't really have time anymore to go into today. But so we're very happy with this agreement from an ab initio calculation. All right, so yeah, so we have a kind of a direct observation of the superfluid speed of sound using single impurities this time. With this, I'm finished, and I would like to thank really an amazing team that stands behind all of this work. In particular, Zoe, who is now a postdoc with him in Princeton, as well as Ichi. He's now the senior PhD student, and our two younger PhD students, Alex and Eric, and of course Martin, who is our fearless leader that makes sure that we are constantly working at maximum motivation, as well as our theory collaborators, Kushal, Pavel, and of course Eugene. And with this, I would like to thank you for your attention. And yeah, if there are any further questions, please don't hold back.
Questions?
May I ask a question?
Yes.
I have actually a few, first, could you comment, I was just curious, can you comment on the effective mass? And can you extract some information about that?
Excellent question. Thanks for asking this. So this effective mass is one of the reasons why we started doing dynamics, because we were very curious to measure this. I can't comment on a measurement, because it turns out that for various reasons, we don't see an effect of the effective mass. So naively, you would expect maybe in the dipole oscillations, or in the dipole oscillations, you would expect the Polaron effective mass to show up as a slightly different frequency of the fermions, right? But indeed, it seems that in a finite temperature system, it's always going to be very hard to measure this, because the thermal excitations of the Bose gas will very, very quickly dampen out any higher frequency. And so indeed, we only see the fermions respond to the boson frequency at sufficiently high interaction strengths where you would be interested in seeing that. And similar story in the breathing oscillation. Again, at sufficiently high interaction strengths where you would be interested in some effective mass, there is nothing left of the fermion's own frequency. So in that sense, I can't give you a value on the effective mass, and the reason is that finite temperature plays a very big role in these systems.
Thank you. May I ask another question?
Yeah.
So during the first part of the talk, it's very interesting. So I was very much excited to see your results. And I was curious, so you draw this connection to strange metals. And because in strange metals, we know the resistivity kind of do not obey Fermi liquid theory. but we know that in some other metals, I think like in copper, even at high enough temperature, you also have linear resistivity for a bit different reason, like connected
Yes.
to lattice, if I understand correctly. Would you say that your experiment actually might be better connected to copper than to the strange metal, or?
So I would say it is better connected to the strange metal by the fact that the resistivity, as far as I understand, in copper does not go to the regime where you have a resistivity high enough that you have a mean free path that is shorter than the lattice spacing. But I'm not an expert on that, so if I'm wrong on that, please correct me. But that is as far as I understand the problem. Yeah. So it's really the breakdown of the quasi-particle, and that's also what we see.
Okay, so like in this sense, yeah, like you're connecting it to mean phi. I see. Thank you. Breakdown. Yeah, because I was just thinking like regarding to Mara's question, that like you don't see this like in this Fermi Polaron, you don't break the Fermi liquid theory. So I was, yeah, that's why I thought that it might be.
Yeah, I really have. Yeah, I have to get back to that question because I should. I think I should be able to answer that. Yeah.
So about the another question about the dipole oscillation. So here, if I understood correctly, the displacement, the relative displacement of fermions and bosons is in the radial direction, right?
Yes, correct.
So why do you choose that instead of the actual direction?
Same reason. It's a finite lifetime. Yeah, so here we are probing the system in time, and you can see already like at these stronger interaction strengths, you can directly visually see by eye the fermions die as a function of time, right? Just limited by 3 body losses.
Okay, thank you.
Any other question?
Yes.
Just a little bit confused by the reference to the Fermi liquid theory, because it doesn't seem that in your system you actually have a proper Fermi liquid regime, in the sense that you have a degenerate Fermi gas or degenerate Fermi liquid, because the whole idea of the Fermi liquid is that if you have a degenerate regime, then the phase space for scattering of a fermion, it vanishes rather quickly as you approach the 0 temperature limit. And exactly, that's the problem. So there's no degeneracy in fermions. So it is not really, you cannot distinguish by this experiment between a Fermi liquid regime and a non-Fermi liquid regime, because you don't. That's what he said. Yeah, you are right. Okay.
Yes, I think the question was that more related to the fact that that also the Fermi, in the fermionic case, you would have an underlying second order quantum phase transition, and why does this not show up somehow in the Fermi Polaron as well? I think that I 100% agree with what you just said. No question. Yes, it's more the fact that in principle the fermions themselves also have this.
Okay.
Carsten, I suggest you open the chat. Another question is in the chat.
Yes, let me open the chat.
At least statement.
Yeah, so I think I know this calculation. Yeah. I think maybe Mira and I should talk about this offline. I would be very interested to continue this discussion on whether it's linear or whether it goes with t to the 3/4, which is, of course, for me as an experimentalist, very hard to discriminate. I will also say that.
The statement is from Mira. We have a paper. We have a paper. Where we show that there is a quantum blockade at the impurity which prevents bosons piling up on the impurity, reference to a paper in PRL. It's actually not clear that there should be linear T scaling in this system. Our calculations show that it should be actually T to the power 3/4. Well, Okay.
Yes, so I can only argue that if you only look at the thermal excitations and you take scattering from that, you would expect something linear. And I can argue the connection to this underlying second order quantum phase transition. But yeah, so I'm very happy to keep the discussion on that.
Yeah, I didn't want to take too much more of your time because I'm conscious of other people's talks after this. So I just, yeah,
Yes.
I'm happy to discuss later. Yeah.
Well, anybody else want to ask questions? Okay, if not, we thank for this talk and thank for sharing with us unpublished results and work in progress. It's always nice to see that things are happening right now, right here, well, on Earth. And at this point, we stop recording this session. Thank you.